So, counting principles, the second of three related units, right? Excuse me. So the first unit was on, I don't know, which one? You did a test on it yesterday. What did that involve? Oh, sets, yeah. So that was set theory, right? Now we're moving to counting. And even in set theory, there's still some counting, right? Like how many of these, how many are in the intersection and stuff. Counting principle is just to kind of come up with a way to count stuff, whether it involves sets or not. And then the third one is probability. They're all pretty closely tied together, though, right? So sort of same ideas are going to come up. So our goal, so today, so this first step in counting principles is the fundamental counting principle. And we're going to use it to solve problems. So, investigation. Serge lives in Winnipeg. This summer he plans a sightseeing trip that includes visiting his family in Regina. So he's here in Winnipeg, wants to visit family in Regina and Saskatoon. There are many places he might visit on the trip, but he knows he will stop in Regina to visit his brother and then in Saskatoon to visit his parents. He has chosen and mapped out 3 different routes he could take from Winnipeg to Regina, right? So that's shown on the map here, right? You go through Weyburn, go through Brandon, go through Yorkton, and 2 different routes that he could take from Regina to Saskatoon, right? So you could sort of like head north and then wherever that is west, or you can just sort of head northwest. How does the number of routes he has chosen between Winnipeg and Regina, between Regina and Saskatoon, relate to the total number of routes that he could take? Right. So how many routes does he have to go from Winnipeg to Regina? 3. And how many routes does he have to go from Regina to Saskatoon? 2. Okay. So what we want to look at is sketch Serge's map and label the highlighted routes from Winnipeg to Regina and Regina to Saskatoon as A to E. So we can just kind of do this off to the side, or you can just do this on a blank piece of paper, right? So we've got, here's Winnipeg, here's Regina, here's Saskatoon, right? And so we've got this route, this route, this route, and then this route, this route. Okay, and if we label them, so let's call this is route A, this is route B, this is route C, that's D, and that's E. Okay, so we've got the 3 routes from Winnipeg to Regina and the 2 routes from Regina to Saskatoon. Complete an outcome table to show the sample space for this situation. Okay, sample space. They define sample space. Describe the sample space for this experiment by listing all the possible different outcomes. Well, must have defined sample space earlier, right? Probably in the first chapter. So sample space is just a listing of all the possible outcomes, right? So it's everything that can happen. So we're going to draw a little outcome table and show the sample space, right? So we're going to say, using our thing here, right? We've got kind of from Winnipeg to Regina, so W, Winnipeg, well, so we got from Winnipeg to Regina, and we could take A, B, or C. And we've got from Regina to Saskatoon. I don't know how to abbreviate that. Let's say Sask is D or E. So in the outcome table, we just say, well, if you took route A and route D, then we'd say you're doing AD. If you took route A followed by route E, we'll say you're doing AE. Here, we're going to do BD, and here BE, and here CD, and here CE. So how many outcomes do we have then? There's a total of 6 different routes that he can take, right? He could take route A followed by D, or he could do A followed by E. He could take B followed by D, or he could do B followed by E, and he could do C where this is A, the upper one, and B in the middle. And you could do C followed by D, which would be going this way, or you could do C and then take E. So clean outcome table, count all the possible routes, so we could list them all, right? So there's A, D, A, E, B, D, B, E, C, D, C, E. To relate it back to set theory, we could throw some brace brackets on there and list. So now we have the set of all possible outcomes, which is the definition of sample space, right? Sample space is the set of all possible outcomes, right? So that's every route that he can take. And how many are there? There are 6, right? So if we said this was set R, let's say, R for routes, then the number in R is equal to 6, right? Number of outcomes in the sample space. The number of routes that he can take. Draw a tree diagram to visualize and count all the possible routes you could take from Winnipeg to Saskatoon through Regina. Okay, so here's how a tree diagram works, right? So we would say, okay, you're starting in Winnipeg, and you can take route A, B, or C. And that's going to get you to Regina. From Regina, you could take route D to get to Saskatoon, or route E. So that's if you took A and to get to Regina, then you could take D or E. And you can see it's called a tree diagram because it's branching out. If you took route B, then you could take D or E. And if you took C, then you could take D or E. Now in a tree diagram, if we follow each branch, we can generate each of the outcomes, right? So you could say, well, this branch is AD. And this branch is AE. And this branch is BD. And this branch is BE. And this branch is CD. And this branch is CE. Now, following each of the branches, we've listed the 6 possible outcomes. We've listed the sample space, right? And sometimes we don't care about the sample space. We only care about the number of things in it, especially if it's like really large, right? It's like, well, I don't care to list all 30,000 ways of doing something. I just need to know there are 30,000 ways to do something. Okay, so tree diagram. Again, you just list. This goes left to right because that's how we read. Right, so you've got route A, so Winnipeg to Regina, route A, route B, route C, Regina to Saskatoon, D or E, D or E, D or E. So on the previous page, we've got the outcome table, right? And we're still getting the same 6 outcomes, right? Outcome tables are nice when there's only 2 things, right? Because you can't do them if there's more than 2 things, right? Like if there was a third, if we were going Winnipeg to Regina, Regina to Saskatoon, then Saskatoon to Calgary or something, you can't list that in this table, right? Because it's not 3-dimensional. We could make a 3-dimensional thing and do that, but we could do it on a tree diagram. If we then had route Saskatoon to Calgary, we could just grow the tree. So the tree can grow kind of infinitely, right? We can have a 3rd choice, a 4th choice, a 5th choice. An outcome table can only deal with 2. Now, let's think about adding a 4th route from Winnipeg to Regina through Dauphin and Yorkton. So in this case, you know, he could go along here, or maybe he's going to go up and there. So there would be one of the routes, and then here would be another one of the routes. Some of it's the same, right? But he's visiting different. He's going through Dauphin on that one. Make a conjecture about the number of routes he can now take from. So if he adds a 4th route here, how many is he going to have in total? How many possible routes? So we still have 2 here, right? That's 2. Now we have 4. Before we had 3 and 2. And 3 and 2 gave us 6. So what's 4 and 2 going to give us? 8. Yeah. So if we went here and we added a 4th root, which we will call f, then we'd still have DE, and we would get FD and FE, and we would see that we've got 2, 3, 4, 5, 6, 7, 8. Okay, so we can add the 4th root. If we went back to the table and added a 4th root here and called F, we would get FD, FE. So we can redo the table, add on to there. We can redo the tree diagram, add on to there. But here, make a conjecture about how the number of roots between Winnipeg and Regina and between Regina and Saskatoon relates to the total number of roots. So in the original, we had 3 roots here, 2 roots here. How do we get from 3 and 2 to 6? What are we doing? 3 times 2, right? So we're saying, well, for each of these 3 roots, there's 2 here, right? So it's 3 times 2. If we added a 4th root, then we've got 4 times 2, right? We're just multiplying. Let A represent the roots from Winnipeg to Regina, and B represent the roots from Regina to Saskatoon. So what expression would we use to have the total possible number of routes from Winnipeg to Saskatoon? Right. So little a was Winnipeg to Regina, and little b. So total roots is what? A times b, right? Total roots is A times B. What type of reason? That's an inductive reasoning. We're looking for a pattern. When figuring out the total number of roots, which applies? Do we need to consider the number of roots from Regina to Winnipeg and the number of roots from Regina to Saskatoon? Or do you consider the roots from Regina to Winnipeg or from Regina to Saskatoon? So this one or this one? Are we doing an and or are we doing an or? And to be safe. And for the win. It's this one, right? Because what we need to do is we need to get from Winnipeg to Regina, and then we go from Regina to Saskatoon, right? It's not an or. Okay? It's not we go from Winnipeg to Regina or we go Regina to Saskatoon. We have to do both, right? We have to stop in Regina. Okay? So the conclusion we're looking at is if we use and, then we are going to multiply numbers, right? And multiply the numbers. Advantages, disadvantages, 3 different methods. So the outcome table, that'll only work if there's 2 things going on, right? It won't work for more than 2. Tree diagram will work for more. Calculating, a lot easier if we just need to know how many, but we don't need to list them. Okay? So if I just care about how many outcomes there are, like for example, we go to Peter's Drive-In and there's 31 possible flavors for milkshakes, right? And we're not going to list them all. Right? Like, what if you got 3 flavors, right? Or what do they allow? They allow 3, right? You can have up to 3 flavors in a milkshake. So, do you want to list all of those? You know, there's too many, right? There's too many to count. There's too many to sit down. Right? Think about it. If I drew a tree diagram, I would need 31 branches. Right? And then, after I pick the first flavor, I'd have 30 choices for the second flavor, right? We're not going to double up on flavors. And after I pick that, then I'd have, right? That's a lot. You're not going to list them all, right? Nobody expects anybody to sit down and list all the possible ways of getting the 31, if there's 31 flavors and you can have up to 3 in a milkshake, nobody expects anybody to sit down and list them all. So, need another way. Selecting Hannah plays on her school soccer team. The soccer uniform has 3 different sweaters, red, white, and black. Well, it's not this school, we don't use red, white, and black. And 3 different shorts, red, white, and black. How many different variations of the soccer uniform can the coach choose from for each game? Okay, now, Hannah's solution using a tree diagram. If you wanted to do a tree diagram, because there's not a lot of possibilities here. So, if we do a tree diagram, then we say, okay, what do we got? We got a sweater and we got shorts. So sweater and shorts. And for the sweater, I can choose red, white, or black. If we're wearing the red sweater, what color shorts can we wear? Red, white, or black. If we choose the white sweater, what color shorts can we wear? Red, white. If we choose the black sweater, what color shorts can we wear? Red, or white, or black. Now, if we list the outcomes, maybe we want the sample space. Hey, we can wear the red with the white, or so here we can wear the red with the red. And here it'll be red with white, and here red, black, and here it's white and red, white and white, white and black, and here it's black and red, it's black and white, and black and black. So how many outcomes are there? There's 9 possible outcomes, right? This is the sample space. Sample space. It's a list of all the possible outcomes. It's not a big deal when there's only 9 things, right? It doesn't take that long to list them. Using a tree diagram gives you a systematic way to list them, right? You don't have to sit down and say, well, so you have the red with the red, or the red with the, right? By doing the tree diagram, you just follow the branches, okay? And you don't miss anything. If you're not doing a tree diagram, you're trying to list the 9 ways, you can be sitting, no, wait, I've already got that, right? Well, but I don't, what am I missing? You'd be looking for it, right? So here's a tree diagram, and here's a listing of the outcomes. Okay, and again, it's just following each thing, each branch. But if you want to know how many ways, then what do we say? How many choices are there for the sweater? And how many choices are there for the shorts? And 3 times 3 is 9. So that leads us to what's called the fundamental counting principle. Number of uniform variations U is related to the number of sweaters and the number of shorts. U is equal to the number of sweaters 3 times the number of shorts 3, which is 9. Okay, and that's called the fundamental counting principle, which is then scooched in down here. Fundamental counting principle says if there are A ways to perform one task and B ways to perform another, then there are A times B ways of performing both. And we could add to that, right? If there were C ways of performing a third. So if C ways of doing a third, then you'd list A times B times C, and so on, right? If there was a 4th task, we would multiply it by it. Next season, coach is adding a 4th style for the shorts, red/black stripes. Create an organized list. No, forget it. It's just how we're going to count. If we have 3 choices for sweaters, that was first, right? So sweaters, and now we have shorts. So 3 choices here. If we add a 4th style, then we end up with a total of 12 different possible uniforms, right? So 3 times 4. That uses the fundamental counting principle. So we're solving a counting problem by extending the fundamental counting principle. So you've all seen these digital locks, right? Got the numbers there. So a luggage lock opens with the correct 3-digit code. Each wheel rotates through 0 through 9. How many different 3-digit codes are possible? Okay, so here's how you do a fundamental counting principle problem, right? You put down 3 blanks. Okay, and you say first digit. Okay, what we don't want to do is do a tree diagram, right? Because we'd have 10 branches and then, yeah, and it's too much. Second digit and third digit. Okay, how many choices are there for the first digit? It could be 0 through 9. So there are 10, right? 10 choices. How many choices are there for the second digit? 10. How many choices for the third digit? 10. 10 times 10 times 10 is 1,000 choices, right? 10 times 10 is 100, times 10 is 1,000. So there's 1,000 different codes that can be used. Now, it says suppose each digit can only be used once, so you can't repeat digits. Okay, and we got to go back up here, and let's erase that. And let's erase this and this. So we still have first digit. So how many? So for the first digit, we still have 10 choices, right? We haven't used any of them. For the second digit, okay, so I had 10 for the first, but we used one. There's only 9 left. Okay, so we had 10, we used one, there are 9, we used another one, so how many are left for the third digit? 8. And 10 times 9 times 8 is 720. So if you can't repeat, so you're going to see that, right? You're going to see the words with repetition or without repetition, or something that implies that thing, right? You can use the same digit more than once. It's like with repetition that allows me to repeat. Or you can't use a letter more than once. That says without repetition, right? I can't use it again. Here's Jake's solution. I like the idea better of putting down blanks with multiplying between them, right? So then you lay it out and you say, okay, there's 3 things I'm doing. And I have this many choices for the first, and then the second, and then the third. And then there's the 720. Suppose you buy a bicycle lock that opens using a 5-digit code set by rotating 5 wheels, 0 through 9. Which lock would be more secure? The one that allows repeating digits or the one that doesn't? Allows. Because how many combinations are there going to be? How many different? Well, okay, we got 5-digit code, right? 1, 2, 3, 4, 5. If I can repeat, then how many for the first digit? Second digit? Third digit? Fourth digit? So 10 times 10 times 10 times 10 times 10 is? We got 100, 1,000, 10,000, 100,000. If we can't repeat, then what do we get here? 10, 9, somebody has to do that for me. I can't do this.
20 times 7, that's 16.
30240. So you can see that if you don't allow repetition, you're cutting out almost 70,000, not quite, right? You're cutting out 69,760 possible combinations by not allowing repetition, right? Now sometimes we can't repeat things, right? So we just have to keep that in mind. So that means you got to deal with what are called restrictions, and the restriction here is you cannot repeat digits. Okay, so that means 10, and then 9, and then 8, and then 7, and then 6. Okay, I'm just going to pop forward. Okay, before we get into the cards, let's do a couple more. So I mentioned that, so Peter's Drive-In has 31 different flavors, right? At least I think they do. Anyone know? Has there been a, let's pause. Flavors. Milkshake. It's actually 31 different milkshake flavors. Oh, there's bubblegum, and there's licorice, and there's cherry, and lime, and lemon, and there's vanilla, and chocolate, and maple walnut, and butterscotch, and so on. There's like 31 of them. Now, you can have from 1 to 3 flavors in your shake. So you can have from 1 to 3 flavors in your shake. So the question is, how many different milkshakes can you make? Different. milkshakes. Right. And then we can figure out, okay, so if you decide you're going to have one milkshake a day, then how many days could you go before you had to repeat? I already had one of those. Okay, so we actually have to deal with a few different conditions here, right? We could have just a one flavor shake. How many one flavor shakes are there? Okay, so one flavor shake. There are 31 of them, right? Because there's 31 flavors. What do we do a two flavor shake? Two flavor shakes. Oh, great. So we ran out of ink. Flavor shake. Okay, two flavors. I need two blanks. What goes in the first? How many choices do I have for the first flavor? 31. How many choices for the second flavor? How many? 30. You're not going to repeat. You don't get to double up on chocolate. It's still going to be just chocolate. Okay? So what's 31 times 30? 930, right? Okay. Three flavor shakes. Does it matter what order I choose the flavors that I'm putting in my shake? No, they're all going to get mixed together anyways, right? Does sometimes when we're choosing things, does it matter the order we choose them? Okay, so if I'm getting a two scoop ice cream cone, it may matter to me whether chocolate's on the top and then vanilla. Like, do I want to start with chocolate and work my way into the vanilla? Or do I want to start with vanilla and work my way into the chocolate, right? So in that case, if I'm going to Baskin Robbins and I'm getting a triple scoop or whatever, then I may care about what order these things are in, right? It's still not going to change the number of them though, right? Okay, first flavor, how many choices do I have? 31. Second flavor. Third flavor. What's that work out to?
29,000.
29,000?
26,000.
26,000. Okay, read me the numbers. 26970.
70.
Okay, so what do all these add up to then? How much? 29,3,1. Okay, so there's about close to, just under. I think they actually say there's more than that, so they must have more than 31 flavors then, right? Like they said, there's over so many possible combinations. But if there were 31 flavors, that's how many. So divide that by 365. What do you get? How much? 76.5. So you could go 76.5 years, assuming that if you had a milkshake every day, you'd live to be 76.5 years old, and never repeat a flavor or a combination, right? You go over 76 years without ever having to repeat. In which case you might actually need the sample space so that you could list and know that I've had this one, right? It's like, I'm going to take a month, I'm going to take a long month, and I'll have every flavor for a day, right? I could do that, 31 days, okay? Maybe not in January, they could be closed on the 1st. Okay, take it carefully. Not December, they're probably closed on the 25th. But July, sure, they're going to be open all of July, right? So 31 days, right? And then you work your way through. Right. Then for the next 930 days, so for the next 2.5 years, I can have my different chocolate, vanilla, chocolate. Right? Yeah, we're probably not going to list them all, right? There's nobody going to sit down and, hey, write out all the possible no, right? I'll pay $1 for each one. Okay, I might do that. For 27 grand, but I don't know how long it would take me, but I think it would be worth my while. In that case, you better just make a big tree diagram, right? Or sit down and write a computer program. You could learn how to program and write the program. really wouldn't take long with a computer program, right? Yeah, you could very easily list them all, right? It's just going to run pages and pages and pages. Okay, solving a counting problem where so the fundamental counting principle applies there, right? Because you can say, I have 3 different choices, and I have this many choices for my first flavor, and I have this many for my second flavor, and I have this many for my third flavor. Sometimes though we go to count things and we cannot use the fundamental counting principle, right? So we can't say, well, there's 3 things and I get this many choices, this many. So here's a standard deck of 52 cards, right? Now in the cards, we've gone through these before. There are 4 suits, clubs, diamonds, hearts, and spades. 2 are red, hearts and diamonds. 2 are black, clubs and spades. There are 13 cards in each suit. These are called the ranks. Okay, and they go from ace, 2, 3, dot, 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 jack, queen, king. Okay, so those are the ranks. Count the number of possibilities of drawing a single card and getting either a black face card or an ace. Okay, how many black face cards are there? 6. How many aces are there? 4. So how many ways are there of getting either a black face card or an ace? 4 plus 6. We're not multiplying here, right? We're adding. Okay. All we're doing is we're just circling the cards that match that event, right? The event is you got a black face card or an ace. I've circled them all. We just count them up. So we can't use fundamental counting principle, right? It's not like we're multiplying. It's not like if I get the jack, then there's 4 ways of getting, right? Because we're not doing more than 1 card, right? We're just drawing 1 card. If we're doing more than 1 card, then it could be the jack with the ace, you know, and then you'd multiply. But that's not what's happening here, right? Drawing a single card. So you got to watch out for this when you're doing, because all these problems pretty much related to each other, right? Could be drawing 2 cards. Now we'll learn how to handle all of that. So either black face card or an ace, there are 10 cards. Either a red card or a 10. Okay, so hang on. Let's clean this up. So either a red card or a 10. All right. So how many cards are there then? You draw 1 card and it's either a red card or a 10. What's the number? So how many reds are there? 26. How many 10s are there? 4. So is the answer 30? No. Why not? Because we counted 2 of the cards twice, right? We counted them once as a red card, right? 10 of hearts, 10 of diamonds, and then we counted them again as a 10, right? Because there are 4 10s. So if we're circling this, we would just say, all right, just count these, right? So there's 26, 27, 28. Now that's handy if it's all in front of you, right? You got the deck laid out in front of you. So you got 26, right? 27, 28, right? I'm not going to count these guys again. Not so handy if you don't have the deck laid out in front of you, right? So you got to think about, well, so what's happening here, right? What's going on? The first time I just added them, right? We just said, hey, we got 6 of these, you got 4 of these, that's 10. Right? We didn't worry about why, because they didn't overlap, right? There was no overlap between the face cards and the aces. Right? A card can be a face card or it can be an ace, it can't be both. But a card can be red or a 10 and it can be both, right? There are red 10s. So we've got to watch out for that. So here's event A, draw a black, right? It's 2 circles, disjoint circles, right? You're either a face card or you're an ace. There's no overlap between them, right? So the number, where'd that go? The number in A union B is just the number in A plus the number in B, right? Number in A union B is 6 plus 4 or 10. There are 10 ways, right? Just to add them up, right? Just A union B is using the word or. It's in A, it's a face card, or B, it's an ace, right? And it can't be both. But when we go to do the second one, draw a red card or a 10. So now we've got a circle representing, C represent the red cards, and D represent the 10s. Now we got a problem, right? There are cards which belong to both circles. So if we want to work out the number in C union D, right? Now, if we're just doing this, we could just count. Like if they're in front of me, I say 1, 2, 3, 4, 5, 6, and 6 of ours is 24, 25, 26, 27, 28. Right? That's why I told you guys. That's what we would do. Our strategy would be just to list how many are in this, how many are here, how many are here. That's a little tougher here. So the number in C union D here is the number in C plus the number in D minus the number in the intersection. Okay. So if I'm doing an OR, and you think this would apply to any of the stuff we did in the last chapter, right? You don't have to worry about it. I didn't even want you using that formula at that point. When you think about it, okay, if I take all the ones that are in C and add to it all the ones that are in D, then I have double counted the ones that are in the intersection. So number in C union D is the number in C plus the number in D minus the number in the intersection. Okay, and this way we don't have to worry about, just look, there are 26 red cards. There are 4 10s. Oh, but wait, 2 of them are both red and 10. This would be an and, right? So this is number that are red plus the number that are 10s minus the number that are red and 10. Right? We just got to think, how many red 10s are there? Okay, there's 2 of them. Right, then we can do this. 26 plus 4 minus 2, or 28. Okay, that's using the formula, right? And here, just explaining, right, there's an overlap. And okay, 28 ways. Suppose you want to determine the number of possibilities of drawing a single card and getting a club or a red card. Okay, are there any clubs which are also red? No. Okay, so if we do this, the number that are club or red, okay, so the union, right, we're putting them together, making a larger number of them, will be the number of clubs plus the number of reds, and there's no intersection. I don't have to subtract off all of the red clubs, because there aren't any. How many clubs are there? How many reds are there? How many cards are there? You're just a moving finger. A heart or a 2. So the number, heart or is a union, is 2. It's the number of hearts plus the number of 2s. Are there any 2s which are also hearts? So it's going to be minus the number that are hearts and, right, or the intersection. So how many hearts are there? How many 2s? How many 2 of hearts are there? Okay, so there are 16 cards that match that, right? It's a heart or a 2. And for counting cards, this is really the easiest way to do it, right? You don't have to worry about laying them out or trying to imagine them, right? Because you're not going to get a deck of cards on the test. You're not going to get that diagram showing all the cards on the test. You just know there's 13 of each suit, and you know the different characteristics that are going on. Okay, so we get 2 different formulas. Now these are on your formula sheet. Just instead of using an N, they use a capital P, and they're for probability, and that's why this is very closely related to the probability unit, right? You can use the same formula. Any of the formulas for probability you look at, you can replace it with a little n to count how many. Okay, so you need to very carefully read the question. They're asking me the probability this happens, which we're not going to do until next unit, or are they asking me how many ways can this happen, right? How many possible outcomes are there? Fundamental counting principle applies when tasks are related by the word and. Okay, and these tasks are related by the word or. Okay, so if we're doing ors, we are not using the fundamental counting principle. If we're doing and, then we can use the fundamental counting principle. Fundamental counting principle states that one task can be performed in A ways, another task in B, then both tasks can be performed in A times B. Okay, well actually we'll do an example too. I want to do one more example before we leave. Fundamental counting principle can be extended to more tasks, so A, B, C. Fundamental counting principle does not apply to tasks when related by the word or. If the tasks are mutually exclusive, both can't happen, right? So both can't happen. That was, well, let's back up a little bit more. Both can't happen is black card or black face card or an ace. There are no black face cards which are aces, right? I mean, you're either an ace or you're a black face card or you're some other card. You can't be both. Red card or a 10, not mutually exclusive, right? Because there are red 10s. Okay, then same thing on this page, right? Club or a red card, mutually exclusive. There's no overlap, right? If we tried to do this and said, oh, let's put in minus the number that are clubs and red, that would just be 0, right? So if this number is 0, they are mutually exclusive, right? There is no overlap, in which case we don't need this. But this formula exists as well. Okay? You could always just use this formula because if they're mutually exclusive, this will be 0. And then you won't have to worry. It's like, okay, I'll add 13 plus 26, and I will subtract. Let's make the equal sign. Take 13 plus 26 minus 0. Okay, it's still going to be 39. Okay, two formulas. The one that is mutually exclusive, so there is no overlap, right? And just think, mutually exclusive just means if you draw it in a Venn diagram, there's no overlap, right? Or there's nothing in the intersection. Not mutually exclusive sets are not disjoint. There is an overlap, right? And in other words, and we'll count something twice, right? Once as part of this set, once as part of that set, and we need to subtract it off. Principle of inclusion and exclusion must be used to avoid. Now this is where we're actually going to allow you to use it. You didn't need to use it in the last unit. Outcome tables, organized lists, and tree diagrams can also be used in solving counting problems. They have the added benefit of displaying all the possible outcomes, which can be useful in some problem situations, but they're difficult to use when there are many tasks involved or a large number of possibilities. We're not going to draw a tree diagram to list the 27,931. No. Not going to do that. Okay, so let me ask you just a couple of questions here. Say, given the digits, zero through 9, period, or maybe a colon, A, how many odd 4-digit numbers are there? Okay, now this one uses the fundamental counting principle, right? You count back, because you say I've got the first digit and the second digit, right? And the third and the fourth. Not first digit or the second digit. We've got a first digit and a second and a third and a fourth. Okay, so we can multiply. So digit 1, digit 2, digit 3, digit 4. So first, second, third, fourth. Okay, if a number is odd, what's the characteristic that it has? It's not divisible by 2. So that means it's got to end with what? Not a 2, or a 4, or a 6. So what does it end with? If it's odd, it ends with 1, 3, 5, 7, or 9. So how many choices do we have for the last digit? 1, 3, 5, 7, 9. 5 choices, right? That's the first number we have to fill in. So here's the thing. Sometimes when we're using fundamental counting principle, with restrictions, we're not filling in, we're not just saying, well, okay, there's 10 digits that can go here. That's not true. Right? We have a set of 5 digits, one of which must go here, so we have 5 choices, right? That's number 1. There are 5 choices because this must be odd. 4th digit must be odd. Must be odd, right? Which is 1, 3, 5, 7, or 9. Okay, now, it's got to be a 4-digit number. What can't you lead with? So the first digit can't be 0, right? So if I said, hey, I've got a number, it's 0397, you'd say, that's 397, right? You wouldn't count that as a 4-digit number. So the first digit, this is the second thing we fill in. because it can't be equal to 0. All right, so let's hang on. We got to figure this out. So there are 10 digits, right? These are the even ones. These are the odd ones. Okay. I have used one of the odd digits, and these are the even ones, and this thumb is 0, so I can't use it. So how many choices do I have for that first digit? There are 8 choices, right? Remember, we started with 10 digits, and we used one here, right? One of the odd ones. Okay. Odd digit is gone, leaving me with 4 odd digits. I have 5 even digits, but I can't lead with 0, so it's out. So there are now 8 numbers that can go in this first place. Okay, let's back up. We started with 10 digits. We got rid of one of the odd digits. We can't use 0. We got rid of one of the even digits. What happens to 0? It comes back in now, right? We can use it. So now how many choices are there for here? There are 8. Right, so think about it. There are 10 digits. We used one here. One of them's gone. I've got 9 left, but I can only use 8 of those 9 because I can't use the 0. Okay, so I use that. Now I've used 2 digits, so I have 8 digits left, but there's no restrictions now, right? Because the 0 comes back in. So 8, and then how many get to go here? Oh, and by the way, we're just saying how many odd numbers are there with no repetition. Okay, there, with no digits repeating. Should have specified that to begin with, right? Because if you could repeat digits, then yeah, it wouldn't matter. Okay, so no digits repeating. I've used 3. There are how many left? 7. Okay, so that's 64 times 5. Where's that? 3,000.
2,240.
2240. 2240. Okay. Now I can ask you how many even digits there are. You can't figure it out like this unless you do 2 steps. And the problem is 0, right? 0 is an even digit. But if you end with 0, then you don't have to worry about starting with 0, right? So if I want an even 4-digit number, I got my 4 digits. I write down my 4 blanks. It's got to be even, right? That means it's 0, 2, 4, 6, or 8. Okay, so I'm going to take one of those. All right, I got 5 choices. The problem is, well, what if the 0 ended up there? It's no longer available to go up front. I don't have to worry about it going up front, right? So then you got to do 2 different possibilities. I've got a 0 at the end, or I don't have a 0 at the end. That's a pain. So, you know what's easier to figure out? How many 4-digit numbers are there? If I don't care if they're even or odd, just how many 4-digit numbers are there? So, B. How many 4-digit numbers? 4-digit numbers with no repetition. Digit numbers with no repetition. Okay, so I put down my 4 blanks, right? Okay, are there any restrictions? What can't we have? Can't have repetition. Also, it can't start with a 0, right? The 4-digit number can't start with 0. Okay, how many non-zero numbers are there that can go in that first place? So I've got 10 numbers. Here's 0 out. So how many numbers are 9? How many numbers are there for second place? Okay, so 10 digits, 0 can't go in, but I get to choose it. Now I choose this number. What happens to the 0? Comes back into play. How many go here?
9.
9. Then.
Why is that 8?
Which one?
The third one.
Okay, you can't repeat and you've used 2 digits.
Oh, yeah.
Right? There's 10 digits, but you say, well, I can't use 0 to begin with. Okay, so I got 9 choices. Okay, so I choose one of the other 9. Okay, I choose you. 0 says, hey, I'm available now. Okay, so now there's 9. Okay, now a number's gone, now there's 8, and then number's gone, and there's 7.
So you can include 10 as a digit.
I include 0 as a digit.
So 0 to 9, right?
0 through 9 is 10 digits. What's 9 times 9 times 8 times 7?
4, 5, 3, 6.
4, 5, 3, 6. How many of these, so of the 4,536 numbers, they are either even or odd. We know how many are odd, so how many are even? What are you going to do to figure out how many even ones are there? Just subtract, right? So even ones are what? 2,296? That's easy. We could get the same number by figuring out the even ones that ended in a zero and the even ones that didn't end in a zero, right? That's just a bit of a pain to me, because that's easy. The no repetition, that's easy to figure out, right? Okay, I can't start with a zero. And so the thing is, when you're doing fundamental counting principle, always deal with restrictions first, right? Oh, it's got to be odd. Okay, then I only have 5 choices for it, right? I don't want to go throw an odd number down and say, well, now there's only 4 choices. No. I have 5 choices, right? It can be 1, 3, 5, 7, or 9. Once that's done, then I go up front, and it's, okay, you can't be 0. Okay, and then after that, after I've dealt with these two, there's no restriction. Here, just one restriction, right? First number can't be a 0. If it is, it's not a 4-digit number, it's a 3-digit number. We don't want that. Okay, work on 2.1.